Hello everyone, I'm Yue Haiyu. The title of my report is Translator and Tokenizer. Firstly, machine translation in multilingual setting faces many challenges. Differences in word order and vocabulary systems across languages often lead to poor translation quality. For example, Chinese relies on word order to express meaning, while Japanese encodes grammar in particles and word endings. These structural differences make it harder for model to understand. Transformer models like BERT and GPT have improved translation quality through attention mechanisms, but tokenization is still crucial. Poor tokenization leads to noise inputs and weak performance, especially for languages like Chinese and Japanese, where there are no spaces between words. In this project, we built a transformer-based Chinese to Japanese translator and experimented with different tokenizers to evaluate their impact on translation quality. We used GPT-4's translation output as a reference baseline to compare the performance of each approach. Finally, we trained a custom BPE tokenizer. We used the Japanese-Chinese parallel corpus and tokenizers from JParaCro, which provides a large-scale sentence pair for supervised training. Then we built vocabularies using touch test vocab, including special tokens like beginning of sentence and of end of sentence. The model we introduced is a transformer-based sequence-to-sequence model, and the special tokens help the model understand the sequence. Special tokens are essential in sequence modeling tasks, as shown in this example. Since the model can't inherently recognize the beginning and the end of a sentence, we add BOS, which is the beginning of sentence, and the EOS, the end of sentence tokens to each sentence. In addition, we use pad tokens to align the length of sequences within a batch so that they can be processed in parallel by the model without shape metrics and unnecessary attention to padding regions. Our model is a transformer-based sequence-to-sequence model. It consists of two key components unique to test models: token embedding and potential encoding. And the token embedding is that converts each token into a dense vector representation, enabling the model to capture semantic relationships between words. And for the positional encoding, as transformers process input is in parallel rather than sequentially. Potential encoding are added to inject information about the order of tokens in the sequence. This allows the model to understand the sequence structure and word order. Our task is designed as follows. We will translate the Japanese sentence. "Kyo wa totemo ii tenki desu," which is the weather is a very nice today in English. First, we displayed the tokenized version of this Japanese sentence and its English translation. This helped to visualize how tokenization breaks down the sentence into small units that the model will process. Then we do experiments with different models. We train another translation model using the same setup as previous discussed, but this time using the Jeba tokenizer for tokenizing Chinese context. Then we perform translation using GPT-4 and use the GPT-4 translation result as a reference to compare the performance of our own trained models. The results of the experiments are shown on this slide. As we can see, a translation based on JParaCro is accurate, but it differs from the GPT result. The JParaCro model uses a single character word for vary, while GPT uses a two-character word to express the same meaning. On the other hand, the translation based on Jeba tokenizer uses a two-character word for vary, similar to GPT, but introduces an incorrect word, which means photo, into this sentence. At the same time, we also observed that the two translators we trained have different tokenization granularity rates. One tokenizes at the character level, while the other tokenizes at the word level. The character level tokenization is similar to GPT's tokenization method, which needed to learn relationships between tokens and construct multi-character walls. On the other hand, the word level tokenizer groups tokenize by words and form sentences. As we can see, with the same training sets, with the same training settings, the model using character level tokenization gets higher accuracy, but has lower translation fidelity. The word level tokenization model, on the other hand, produces translation closer to GPT's result in terms of fidelity, but it introduces wrong word into the sentence, which should not be there. Next, we explore further research by training a new tokenizer using BPE. BPE works by repeatedly merging the most frequent pairs of characters in the vocabulary. This process continuing until we reached desired vocabulary size. The main benefit of BPE is that it reduces the vocabulary size while still allowing the model to handle real or unseen words by breaking them down into smaller units. The BPE consists of five components. The BPE model consists of five components. First is, of course, the BPE, and the second is the normalizer. It processes the test before tokenization, such as removing accents or converting the test to lowercase. It helps to standardize the input and removes any unnecessary noise. And the third is a pre-tokenizer. Its component splice the text initially, usually based on spaces, punctuation, or numbers. It ensures that the text is segmented properly before feeding it into the model. Then is the post-processor. After tokenization, post-processor adds special samples, which are used to indicate sentence boundaries or provide context. Finally is the decoder. After the model has processed the tokens, the decoder converts the tokenized IDs back into human-readable text, and we can see the model's output. Then we can see the results of the tokenizer we trained, as shown in this slide. While the output tokens might not fully align with Chinese tokenization rules, they do follow the logic of BPE. Similar to how BPE extracts the common subword today from the word like today and yesterday, it tracks 天的 from 今天的 and 昨天的 or 后天的. It identifies repeated patterns or subwords across different contexts to improve the model's efficiency in processing language. That's all the work I did, and that's all. Thank you.